Evaluate limits of polynomial functions at infinity. Alright, so first we need to talk about limits at infinity. But before we do that, let's just do a brief review of what we know about limits. So, as we know so far, limits can be used to describe the behavior of a function. And so far, we have used limits to describe the behavior of a function at a single x value, because up until now we've been taking the limit as x approaches a single number a. And this has been great because it's allowed us to define continuity at a point, describe different types of discontinuities, and how the function behaves at these particular discontinuities. So for example, we've investigated removable discontinuities, and with removable discontinuities, we know that the limit from the left is going to equal the limit from the right, and they're both going to be at that same point. And we can say that, okay, well, if there is a removable discontinuity, the limit exists, but the limit doesn't equal the actual height. We've also looked at jump discontinuities, where the limit from the left does not equal the limit from the right, and that's a dead giveaway for us. That's a jump discontinuity. And we've also talked about that when limits approach infinity, or negative infinity, that means that there's going to be an infinite discontinuity, or a vertical asymptote. Next up, we'll be talking about using limits to determine and describe the end behavior of functions. Now, what is end behavior again? Well, let's remember that end behavior describes the behavior of a function at the ends of the x-axis, i.e. negative and positive infinity. So looking at our graph, where will we be looking for the end behavior? Well, we'll be looking at the graph as x goes towards infinity, and then as x goes towards negative infinity. And since infinity is not a number, it's the idea is that the numbers get farther and farther and farther away from the x-axis, or grow forever and ever and ever, we're no longer looking at the limit at a specific point. We're looking at the limits forever and ever and ever. So off into infinity. So next up we'll be talking about how to evaluate the limit as x approaches negative infinity and as x approaches positive infinity to determine the height of functions as x gets larger and larger and larger. But wait, before we head into that, we need to do a quick review about factoring, because factoring is essential for solving limits at infinity. So, simply put, factoring is really just dividing out a term from an expression. And we can start out with an expression 2x plus 4. So now let's just quickly review how we can factor this. Now I know this is quite an easy factoring, or quite an easy factorable expression, but the point of this is just to demonstrate factoring, not to go ahead and teach it again. But anyways, if we break this apart, we can see that 2x is really 2 times x, plus 4 is really 2 times 2. Now we can see here that each expression has a 2 in common. So it would be easy for us to factor out a 2. So to factor out a 2, the first thing we're going to want to do is we're going to want to divide both of those terms by 2. And then since we divided them by 2, we have to kind of undo that operation to keep it the same. So we are going to have to multiply this whole expression by 2s, not to change it. And let's see, these 2's will cancel out, those 2's will cancel out, and this is going to leave us with 2 times the quantity x plus 2. Which we can always check to make sure we factor correctly by distributing the 2 back in, and that would give us 2x plus 4. Now, this particular expression was easy to factor because both of our terms had a factor of 2. And that is known as a common factor. They both have the same multiple in common. So factoring works nice and easy here, since each term has a common factor. But what if we don't have a common factor? Can we still factor an expression if we don't have that common factor? And yeah, you better believe it. We can definitely still factor something out. It's just not going to look nice and pretty like the previous example. So we're going to look, and first we're going to factor 3x squared plus 5x minus 1. Now, since we're not looking for common factors, we can choose to factor out anything we want from here. Well, let's just go ahead and let's factor out a 3, because it's the coefficient of x squared. And again, I just randomly chose that. Well, if we are going to factor out a 3, that means we're going to have to divide every term by what we want to factor, which in this case is 3. And then we're going to have to undo all those divisions with multiplication. Simplifying this down, the 3's will cancel out. And this is going to leave us with 3 times x squared plus 5/3 x minus 1/3. And boom! We have it. This is now factored. Again, it doesn't look as nice and pretty as the previous example, but we have successfully factored the 3 out of the expression. And we could always check our work by distributing the 3 back in, and if we did that, we would get 3x squared plus 5x minus 1. So you don't need a common factor in order to factor. It just makes it easier, and in a lot of cases works out nice and pretty. Let's take a look at another example. Let's take a look at x cubed minus 4x squared plus 7x plus 6. And this time, just for fun, why don't we factor out an x cubed from every expression? So that means we're just going to divide every expression by x cubed. And that means we can put, I did the last one by x squared, excuse me, x cubed, and then we can put the x cubed in the front. And then we can simplify. X cubed divided by x cubed is going to be 1. Let's see, x squared divided by x cubed, we can cancel out the 2x's in the numerator with 2 of the x's in the denominator. 7x over x cubed, we can cancel out 1 of the x's in the numerator with 1 of the x's in the denominator. And then the 6 over x cubed, they have nothing in common, so we leave it as is. So simplified, we would be left with x cubed times the quantity, 1 minus 4 over x plus 7 over x squared plus 6 over x cubed. And again, doesn't look so nice and pretty, but it is factored. We were able to factor an x cubed out to get 1 minus 4 over x plus 7 over x squared plus 6 over x cubed. And there we have it, factoring. Now this particular factoring skill is going to be vital to evaluating limits at infinity, and I'll show you why in just a moment. Alright, so let's take a look at our first limit at infinity. And our first one we're going to start off with, we're going to be looking at some nice and simple limits. So we're first going to take a look at the limit as x approaches infinity of x. Now, we know that with limit properties, if we have the limit of x, all we need to do is substitute the a in for the x. And even though infinity is not a number, that process still works here. So we can still apply direct substitution. And we are going to get infinity. So therefore, the limit as x approaches infinity of x is infinity. Woo! Nothing too difficult there. And then next up, we can take a look at the limit as x approaches infinity of x squared. So we can do direct substitution here. We can just throw infinity in, so we'll get infinity squared. And now, since infinity is the idea that numbers get larger and larger and larger, if we take the largest number we can think of and square it, it's still going to be a super large number. So therefore, infinity squared is just infinity. And moving on, we have the limit as x approaches infinity of x cubed. And we can do a similar thing here as with x squared. We're going to get infinity cubed. And infinity cubed, again, super large number cubed is still going to be a super large number. So the limit as x approaches infinity of x cubed is infinity. Alright, next up, we're going to look at these exact same expressions, except now we're taking them as the limit approaches negative infinity. So our first limit, we have the limit as x approaches negative infinity of x, and we'll just do direct substitution here, nice and simple. However, the next one, the limit as x approaches negative infinity of x squared, has some, interesting things to it. But we'll perform direct substitution, so we'll get negative infinity squared. And that's a bad negative infinity. Let me try to write that a little bit nicer. So negative infinity squared. So now we have to ask ourselves, well, wait a second. Negative infinity means we're going in the opposite direction. So if we square it, does squaring a negative infinity make it positive? And I don't know. Let's see and let's take a look. Well, if I wanted to, which I do, I can rewrite negative infinity by rewriting this as negative 1 times infinity squared. Well, since we have multiplication, we know that we can pull apart exponents. So this is going to become negative 1 squared times infinity squared. Well, negative 1 squared we know is going to be positive 1. And we already have said that infinity squared is infinity, so that's just going to be infinity. And then 1 times infinity will give us infinity. So therefore we can determine that the limit as x approaches negative infinity of x squared will equal positive infinity. And then finally, let's take a look at the limit as x approaches negative infinity of x cubed. Now we can solve this one in a very similar fashion as with x squared. So we'll do direct substitution first to give us negative infinity cubed. We can then split the negative infinity up into negative 1 times infinity, and that'll all be cubed. We can break that apart to be negative 1 cubed times infinity cubed. And hopefully remember that negative 1 cubed is negative 1. And infinity cubed we already said is infinity. And then negative 1 times infinity will give us negative infinity. And there you go. Limits at infinity for some nice simple functions. Okay. What if we want to get a little bit more challenging? What about this one? The limit as x approaches infinity of 1 over x. All right, well, our go-to strategy is always direct substitution and see what happens. So we can come in here and we can do direct substitution, and we're going to get 1 over infinity. Okay, well, spoiler alert, we don't know what the value for 1 over infinity is. But fortunately, we can use limits to describe the behavior of 1 over infinity, i.e., we can answer the question, what happens to the value of the fraction as the denominator gets larger and larger and larger? So we're going to look at the limit as x approaches infinity of 1 over x. And well, we tried direct substitution and that didn't work, so let's go to our next option. Let's look at a table. So we'll make a table here, so we'll have x, and then we'll have our f of x value, which is 1 over x. All right, so then let's just choose any x value. I'm going to choose x equals 2. So when I plug that into the function, I'm going to get 1 over 2, which is going to be equal to 0.5. All right, cool. Well, let's pick another number. What about 4? That's going to give us 1/4, which is going to be 0.25. All right, well, let's jump up a little bit. Let's go with 10. That'll give us 1/10, which is equal to 0.1. All right, well, what about 100? That'll be 1 over 100. That'll be 0.01. What about then 10,000? So that will give us an output of 1 over 10,000, which will give us 0.001. All right, what about 100,000? Let's get real crazy. Well, that'll be 1 over 100,000, which is going to be 0.0001. All right, well, we see here that as we get closer and closer to infinity, or as x approaches infinity, we can see that our function 1 over x gets closer and closer and closer to 0. So while we may not be able to determine a value for 1 over infinity, we can say that the behavior of this particular function gets closer and closer to 0, or that the limit as x approaches infinity of 1 over x is 0. And ding, 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 we did it! For the limit as x approaches infinity of 1 over x, that is going to equal 0. And I just want to make one side note here. We just proved that the limit of 1 over x equals 0. We did not show that 1 over infinity equals 0. So that is still not true. 1 over infinity is not 0. But as the denominator gets larger and larger and larger, the fraction gets closer and closer and closer and closer to 0, which is why we need to talk about the limit as opposed to the actual value. Alright, so we just determined that the limit as x approaches infinity of 1 over x is equal to 0. We could do the same thing with the limit as x approaches negative infinity of 1 over x, and if we would do the table, we would determine that this limit would also equal 0. Alright, cool. So that's a couple of things, like right off the bat. Those are nice and simple. Well, if we used our logic for figuring out these limits, we could also talk about the limit as x approaches, the limit as x approaches infinity of a number over 0. Now, since the denominator is getting infinitely large, it doesn't really matter what the numerator is because the denominator will always be significantly bigger, which means these limits will also equal 0. And then finally, if we took the limits as x approaches positive or negative infinity of a number over x to an nth power, those would also equal 0 because the denominator will always be a super large number, therefore beating out the numerator and giving us 0. So these 6 formulas are super important to us moving forward. And speaking of moving forward, let's now take a look at evaluating limits of infinity limits at infinity of polynomials. So our first example we're going to take a look at is the limit as x approaches infinity of x cubed minus x squared plus 1. Alright, so the only real method that we have so far is direct substitution. So let's just plug that in and see what happens. So we're going to get infinity cubed minus infinity squared plus 1, which is going to be infinity minus infinity plus 1. And now we are stuck because of this whole infinity minus infinity thing. Yes, we know a number minus itself is 0, but again, infinity isn't a number. It's the idea that numbers get larger and larger and larger. So how do we take one really large number that we don't know the value of and subtract another large number that we don't know the value of? So therefore, infinity minus infinity, we don't know what that's going to be. Is it going to be positive infinity? Is it going to be negative infinity? It could theoretically be 0. We don't know. So that's where we get stuck. So direct substitution won't work here. So we're going to need to use a different idea here. And here is the big trick to evaluating limits at infinity of polynomials. So we are trying to get rid of the infinity minus infinity. So we're trying to get rid of the infinity. So if only there was a way that we could turn infinity to, I don't know, somehow maybe being 0? And we just happen to find a limit where if we substituted infinity, we would change it to 0. So we're going to have to use the limit as x approaches infinity of 1 over x equaling 0 here. Now, how do we actually do that? Well, let's look at our limit again. So let's say we take the limit as x approaches infinity of x cubed minus x squared plus 1. We're going to want to factor something out of this expression. And the thing we want to factor is we want to factor the variable with the highest degree. So let's come in here and we can factor out the variable with the highest degree. And based on what we reviewed earlier, we know that if we're factoring out an x cubed, all that means is we just need to divide each term by x cubed. So that's going to leave us with x cubed over x cubed minus x squared over x cubed plus 1 over x cubed, which we can simplify this down to be the limit as x approaches infinity of x cubed times 1 minus 1 over x plus 1 over x cubed. Alright, so now we can see that we have 1 over x and 1 over x cubed, And if we play our cards right, we can eventually turn those into zeros. So let's play those cards. So I can rewrite this limit as being the limit as x approaches infinity of x cubed times the limit as x approaches infinity of 1 minus 1 over x plus 1 over x cubed. And I can continue to use my limit properties to get the limit as x approaches infinity of x cubed times the limit as x approaches infinity of 1 minus the limit as x approaches infinity of 1 over x. And boy, am I sick of writing this limit sign, but I have to do it. Whew! And there we go. And that with the limit as x approaches infinity of 1 over x cubed. All right, so how did this really help us? I mean, it really just, hurt our writing hand, and we wasted a lot of this time rewriting the limit over and over again, but it just looks more complicated than ever. And it may look that way, but remember, we know that the limit as x approaches infinity of 1 over x is 0. So this guy is going to be 0. And we know when we have 1 over x to some power, that limit is also going to be 0. So what are we left with? Well, we're left with the limit as x approaches infinity of x cubed times the limit as x approaches infinity of 1. Well, we know that the limit as x approaches infinity of 1 is just going to be 1. So we're just going to have the limit as x approaches infinity of x cubed times 1, which is the limit as x approaches infinity of x cubed. And we already know that with this particular limit, we can do direct substitution to get infinity cubed, or just infinity. So there you go. By being able to factor out the term with the highest degree, in this case the x cubed, we were able to turn a bunch of our terms into fractions. That eventually led us to take the limit of those terms and make them be equal to 0, which got them out of the problem. We avoided the infinity minus infinity case, and we're able to find the end behavior here. So, as x cubed minus x squared plus 1 goes all the way out to the end of the x-axis, our height shoots all the way up towards infinity, infinity, and infinity. So, woo, there we have it, our first polynomial limit at infinity. Let's take a look at another one. So this is going to be a lot quicker because we don't have to do the explanation anymore. So we have the limit as x approaches infinity of 2x to the fourth minus x squared minus 8x. So, like we said in the last problem, the trick is to take the term with the highest degree and factor it out. So that means we're going to factor out an x to the fourth. So that's going to give us the limit as x approaches infinity of x to the fourth times 2 minus 1 over x squared minus 8 over x cubed. And now I skipped some steps here just to make this go a little bit quicker. I did the factoring in my head. All right, then from here we can just, distribute the limit to everything. So we're going to get the limit as x approaches infinity of x to the fourth times the limit as x approaches infinity of 2 minus the limit as x approaches infinity of 1 over x squared minus the limit as x approaches infinity of 8 over x cubed. Then from here, we can see that the limit as x approaches infinity of 1 over x squared is going to be 0. The limit as x approaches infinity of 8 over x cubed is going to be 0, leaving us with the limit as x approaches infinity of x to the fourth times the limit as x approaches infinity of 2. We can then go ahead and do direct substitution, giving us infinity to the fourth times 2, which can be simplified to be infinity times 2. And a super large number times 2 is still a super large number, giving us an answer of infinity. So, just like the previous one, as x approaches infinity, the height of this function approaches positive infinity. All right, next up, we're taking a look at the limit as x approaches infinity of negative x to the fifth minus 4x cubed minus 2x plus 1. All right, so again, we want to identify the term with the highest degree, which is x to the fifth, and we're going to factor that out. So this time we're going to have the limit as x approaches infinity of x to the fifth. And I wrote to the fourth by accident, so let's correct that. X to the fifth times, let's see, we're going to get negative x to the fifth divided by x to the fifth, minus 4x cubed divided by x to the fifth, minus 2x over x to the fifth, plus 1 over x to the fifth. And then we can simplify that all out to get the limit, as x approaches infinity, of x to the fifth times negative 1 minus 4 over x squared, minus 2 over x to the fourth, plus 1 over x to the fifth. Alright, now we can just use the properties of limits and put the limit into everything, which is going to give us the limit, as x approaches infinity, of x to the fifth times the limit, as x approaches infinity, of negative 1. And yes, you have to continue to write all these limits just like I am. It is horrible, it is awful, but welcome to Calc 1. Just think of it as all of this writing makes you look smarter. Am I going to be able to fit this in here? Just barely. Okay, just barely made it. Sorry for trying to cram that in at the end there. But it doesn't matter because this limit we know is going to be 0. This limit we know is going to be 0. And this limit we know is going to be 0. Because all those expressions are limits of a number over a variable to some power, which we know is 0. Alright, so now that is leaving us with the limit as x approaches infinity of x to the fifth times the limit as x approaches infinity of negative 1. And we can evaluate, so this can give us, let's see, infinity to the fifth. The limit of negative 1 is just negative 1. And I got an extra dot in there. Let's get rid of that so we don't cause any confusion. Infinity to the fifth times negative 1. Well, we know that infinity to the fifth is just infinity. And then infinity times negative 1 is going to give us negative infinity. So as our function approaches the end of the positive part of our x-axis, we can see that the height of our function is dropping down as far as it can possibly get from the x-axis. Alright, next up we're going to take a look at the limit as x approaches negative infinity of x to the fourth minus x squared plus 4. And just like all the other examples, we're going to follow the same process. I'm going to take the x to the 4 and factor this guy out. So we're going to have the limit as x approaches negative infinity of x to the fourth times, let's see, x to the fourth over x to the fourth, minus x squared over x to the fourth, plus 4 over x to the fourth. And then I can simplify this bad guy out. So we're going to get the limit as x approaches negative infinity of x to the fourth times 1 minus 1 over x squared plus 4 over x to the fourth. Boom, simplified. All right, get ready, it's limit time. Whew, shaking out my hand, let's hit it. Limit as x approaches negative infinity of x to the fourth, parentheses, limit as x approaches negative infinity of 1 minus the limit as x approaches negative infinity of 1 over x squared. And let me tell you, if you think writing a limit every time is a pain, imagine having to write it and say it every time. That's also a pain. But this is the best part, because we can make some of them go to 0 and bye-bye. Alright, next up we get the limit as x approaches negative infinity of x to the fourth times the limit as x approaches negative infinity of 1, which is going to be negative infinity to the fourth times 1. Let's see, we've already talked about the negative infinity to an even power. We know that that's going to become positive infinity. And then infinity times 1 is still going to be infinity. And just a reminder in case you've forgotten here, this guy, negative infinity to the fourth, remember we can break this out to be negative 1 times infinity to the fourth, which would be negative 1 to the fourth times infinity to the fourth. Negative 1 to the fourth is 1, infinity to the fourth is infinity, and 1 times infinity is infinity. So again, just in case you forgot that from earlier, that's why negative infinity to the fourth power is positive. And let's take a look at one more really quickly. Here we want to take a look at the limit as x approaches negative infinity of negative x to the fifth plus 2x cubed minus x. So I wonder what we're going to do. Probably the same thing we've done in the last 5 examples. We're going to take the variable with the highest exponent and we're going to factor it out. No way, really? Yes way. So we're going to have the limit as x approaches negative infinity of x to the 5th times the quantity. That's a 4th, not a 5th. I don't know why I'm having a problem with writing bios today. And that's going to leave us with, let's see, negative x to the 5th over x to the 5th plus 2x cubed over x to the 5th minus x over x to the 5th. Simplify this bad guy down. That's going to be negative 1 plus 2 over x squared minus 1 over x to the 4th. And then we can limitize it. That's a totally fake word that I'm going to be using from now on, because it's fun to say. Alright, so we did limitize it, and then this guy can go to 0, that guy can go to 0, continuing on the limit as x approaches negative infinity of x to the 5th times the limit as x approaches negative infinity of 1. We can substitute in to get negative infinity to the 5th times 1. Negative infinity to the 5th is going to be negative infinity, and that times 1 will just be negative infinity. Alright folks, that is it. That is polynomial limits at infinity.